Multiverse theory is no longer just a part of a good sci-fi story. There are now some scientific theories that support the idea of a parallel universe beyond our own. However, the multiverse theory remains one of the most controversial theories in science. Today we'll find out where the edge of our universe lies, if the multiverse really exists, or if it's just a philosophical concept. Let's take a closer look. Let's start from the beginning. No, the very beginning. Yes, here, right here, where at some point our universe was born. So where is here? The question is irrelevant because space as we know it does not yet exist. All matter, all that exists, time and space, absolutely everything that has ever existed and still exists was here in one spot. This spot is what we call the singularity. And then the singularity rapidly grew much larger. The Big Bang had occurred. Stop. Let's take a look at the time. By the way, yes, it already exists. And so 10 to the minus 43, perfect. We are in the Planck epoch. Here, we'll draw the line of before and after. We have absolutely no idea about the events, phenomena, and laws of nature before this moment. The singularity remains the most mysterious and unexplained state of the universe for us. All of our theories and formulas stop working. Stephen Hawking explained it as, the results of our observations confirm the hypothesis that the universe occurred at a particular moment in time. However, the actual moment of creation, singularity, does not obey any of the known laws of physics. The singularity appears to be a paradox. In theory, it should have infinite density and temperature, which is impossible in practice because with infinite density, the entropy is approaching zero, which is not consistent with infinite temperature. There are many paradoxes like this one. Let's get back to the Planck epoch. Why is it called this? It took place during the Planck time, the minimum measurable or detectable time span in our universe, from time 0 to 10 to the minus 43 seconds. In this epoch, the fundamental forces of physics, electromagnetic, weak and strong interactions, were combined, kind of like a unified superforce, a super interaction between matter. Due to extreme conditions, this system was unstable, and the unity of force and matter came to an end. The process we call matter asymmetry or baryon asymmetry practically created the physical conditions, constants, and particles that we observe to this day. From our perspective, this fact is unusual to modern physicists because neither the standard model of particle physics nor the theory of general relativity provides a known explanation for why this should be so. What's strange is that physicists predict the Big Bang should have produced equal amounts of matter and antimatter. But in fact, we practically do not see antimatter anywhere. What occurred was the definitive divide into matter and antimatter. Matter became the dominant form of substance in the universe. The disruption of symmetry led to the second stage of creation, the so-called grand unification epoch. At that time, gravitation finally becomes a separate force. The three others are still unified as the electro-strong force. The universe became relatively less homogeneous. There is a shift in its density. The second stage, the grand unification epoch, ends as quickly as it started, around 10 to the minus 36, from the moment of the universe's creation. Next, the combination of various factors led to rapid expansion of the universe. In an instant, a spot the size of a subatomic particle expanded to the size of an orange, and another moment later, to the size of a galaxy. It continued to grow exponentially during the rapid expansion of the universe. Some points in the universe were moving apart faster than the speed of light. This is an apparent contradiction because to emerge is not permitted to propagate through space faster than the speed of light from the perspective of any other observer in the universe. However, according to scientists, this contradiction is resolved because while the distance between objects is increasing faster than the speed of light, the objects are not moving through space faster than the speed of light. It is in fact that more new space is being created in between them. From now on, we will forego a few more epochs of the universe's creation to get back to the main topic of this video. Let's just establish the fact that our universe has a volume, it's homogeneous and relatively cold. The matter that prevails here is familiar to us, and this is practically the universe in which you and I live, except there are no stars and planets yet. But what shape is it? In order to understand how the multiverse works, you need to understand the shape of our universe. It all depends on how dense the universe is. The shape of our universe depends on the numerical value of the density parameter, omega, which is a term appearing in the equations used to model a homogeneous isotropic universe. If the density parameter of our universe is greater than 1, omega greater than 1, the universe is curved like a sphere. If the density parameter is 1, omega equals 1, our universe would be flat. The third possibility is that our universe has a hyperbolic curvature, like a saddle, which is the case if the density parameter is less than 1, omega less than 1. Why is this important? The density parameter can show us how the universe will end. For example, whether it will continue to expand infinitely or will it collapse on itself, whether it will be finite or not. And how do we determine the value of omega? For example, by measuring the density of the universe and the rate of its expansion using the analysis of the cosmic microwave background. Cosmic microwave background, CMBR, is radiation visible in all directions, which is left over from the high temperatures in the early universe. The analysis registers temperature fluctuations of the relic afterglow of the Big Bang. You have probably seen this image more than once. After the Big Bang, there were minor fluctuations in the local temperature across the universe. And these fluctuations are still visible in the CMBR and can be measured to a high degree of accuracy. The presence of this anisotropy in the CMBR both confirms the Big Bang model and allows us to calculate the value of constants such as the density parameter. The result is, our universe is flat. Omega equals 1. The universe is flat because it expands without a positive or negative curvature. Of course, this question is still a source of many debates in the scientific community. To allow us to examine the concept of the multiverse, let's accept the flatness of the universe as fact. All contemporary electronics, from computers and smartphones to robots and space shuttles, would be impossible without the solutions of corresponding quantum equations, which could have not one, but 2, 3, 1,000, or 1,000,000 answers. There are multiple solutions, but in an experiment, scientists always only observe one. Until the result is observed, all solutions are realized, and the particle is in all of its possible quantum states simultaneously. The scientists refer to this as quantum superposition. In 1926, Erwin Schrödinger came up with a short equation that defined every quantum state an elementary particle could be in. The equation worked with one tiny clause. Schrödinger's equation doesn't have a single concrete solution. As soon as the result is observed, there is a single solution. The rest of the possible solutions cease to exist. Their quantum states collapse. The life of the cat depends on the quantum state of a particle. If it collapses, the cat dies. If not, the cat gets to live. It exists in superposition of these quantum states. Swedish-American cosmologist Max Tegmark took the Schrodinger's experiments even further and put forward this unusual idea. What if we can only observe one result of the experiment because the other results are manifested in alternative universes? So how many alternative universes are there? Theoretically, an infinite number. In every universe, there's an observer recording a certain result of an experiment different to the one observed by a physicist in our universe. And if that wasn't enough, Tegmark pushed the concept of the multiverse even further, splitting it into levels. The first level of the multiverse. Universes exist in a single infinite time-space, which means all of them have the same laws of physics and constants. They are, so to say, closest to us, but due to the constant expansion after the Big Bang, they keep moving further away so quickly they have no influence on the processes happening here. At this level, we could discover our doppelgangers, practically identical to us. There's no way to fact-check this. The other universes exist beyond our comprehension. We just cannot measure the status of the system while existing within it. And for this exact reason, Tegmark's theory remained an extravagant fantasy as opposed to being considered a serious scientific thought. That was before traces of the multiverse appeared in the formulas of cosmic inflation after the Big Bang. Second level of the multiverse. The second level is much more intriguing, as it unites a multitude of universes appearing as a result of chaotic inflation, the result of which are multiple Big Bangs. In other words, these are worlds with a different starting point to ours. The fundamental laws of nature in these worlds are the same as in ours, but the constants and elementary particles are different. Subsequently, the worlds have much more variety, infinite variety. There's an infinite number of variations because each of these universes had its own evolutionary development in terms of chemical compounds and physics. Just imagine, in these worlds there are possibilities of stars that never shone, atoms that break down as soon as they form, or the opposite, matter taking form we can't even envision. Third level of the multiverse. This is akin to the multitude of all quantum states in which the universes from the first and second level can exist, all mathematically possible event variations. These universes may reflect alternative outcomes of the past and even future events. To simplify, according to Tegmark, the third level of the multiverse is the space of superposition. Furthermore, if we take a more philosophical approach, we can say this is a certain boundary, after which our fantasy cannot function any further. The third level of the multiverse contains absolutely everything. Any theory, concept, fantasy, state, and parameters of a substance, types of substance, all kinds of constants, and law of physics. Everything that shapes reality. Oh, but we're not finished yet. We're about to dive into the most insane part of this theory. And before we can even approach the fourth level, we must have a small theoretical preface. Think about it. Even in this endless variety of universes on all levels, with the difference in elementary particles, laws of nature, and quantum states, there is something that unites these worlds. Something that remains the same from one universe to the next. We'll give you a few seconds and try to answer yourself. Maths. Every single variation of the universe, without exception, can be defined with maths. And Tegmark tried to explain why. Imagine an apple. Describe it. It's round, red, hard. Great. Now let's take a closer look at this apple, at the molecular or even quantum level. Here, these qualities disappear. An atom is not round, red, or hard. Atoms have no color, and the concept of temperature is not applicable to a single atom. So what qualities does an atom possess? Quark, For example, spin and impulse. But in their essence, both of these parameters are pure abstract mathematics. Immaterial essence, in reality just numbers. If we are to believe the string theory, elementary particles are just vibrations of some strings, and these strings don't even have mass. Their mass is created in the process of the string vibration in so-called Higgs fields. The string is not strictly speaking a physical object, it's purely mathematical, a number. As a result, Tegmark came to a shocking but fundamental conclusion. On the most fundamental level, physics does not exist, only maths. Everything that surrounds is essentially nothing but abstract mathematical concepts. The math does not define nature. Math is nature. Fourth level of the multiverse. The fourth level of the multiverse are realities with different mathematical structures that are entirely different from ours. And when we say entirely, we do mean entirely. In a way, the question of what do they look like or how do they differ is absurd if not pointless. It's a different reality in which maths is different, if it even exists. And if the things that happen in that reality can even be described in any terms relative to maths. But don't forget, this is just a theory that is paradoxical, infinitely complicated and confusing, and therefore attractive, but still a theory. With his radical idea, Tegmark aroused the brightest minds of this world, but he also gained a bunch of opponents to his theory. We are glad that there are radical thinkers like Tegmark striving to answer the philosophical questions that have tormented humankind over the ages. What is time? In a world of mathematics, it's an abstract concept, the subjective nature of which is born exclusively within our consciousness. And what is consciousness? It's an infrastructure in our brain which can be clearly defined by physics and therefore mathematics, which leads to the conclusion it is yet another abstract mathematical concept, and so on and so forth. If Tegmark was wrong and the fourth level of the multiverse does not exist, then one day the scientists will come across an impenetrable obstacle. They will find something that cannot be mathematically defined. And then the science will truly lose its meaning. But if Tegmark is right, the science will never finish. What do we think? Let's express our opinion in the superposition. And we really hope that you're watching this video in the version of the universe where you've received a satisfying answer to your questions. Thanks for watching.